Today we're going to continue with the stroboscope tutorial that shows how to model earth moving for the construction of a dam. This is the first of several successive models. It does not include the soil as a resource. It only concentrates on two resources, the loaders and the trucks. We have two kinds of loaders and we have two kinds of trucks, but at this point we're going to model all the loaders as a single type of resource and all the trucks again as a single type of resource. And we're going to concentrate on the basic structure of a stroboscope model so we understand what the elements are. On this particular page, the graphic itself, the network, shows the stroboscope model as developed in the graphical user interface for stroboscope. The rest of the text, beginning with the line "simple earth moving using generic resources," is simply text that has been placed on the Visio page to explain the main elements of this particular model. In other words, it explains the important stroboscope statements that we will examine in just a moment. The next page shows the actual stroboscope file that describes the first model for this earth-moving operation. The entire model is shown on this page, and the entire model is described as a text file using the statements that we see on this particular page. Everything that begins with a slash, such as the 4 lines at the very top of this file, are comments. So all the statements that follow the slash do not do anything. They're simply there to give the user information about the model itself. So the very first statement is the one that begins with the word variable. The variable statement defines a variable which is similar to a named cell in Excel that contains either a number or a formula. In this case, we have 4 such variable statements. The first one defines a variable whose name is num_loaders and whose value is 3. Notice that all statements in a stroboscope file end in a semicolon. It is the semicolon that actually separates one statement from the next. What we have here are 4 variable definitions whose names are num_loaders, num_trucks, loader hourly cost, and hauler hourly cost, which have the particular values 3, 11, 50, and 135. After that come 2 statements that define the generic types of resources that are involved in this model. The first one is defined by the statement gen type. The name of the resource is loader. The second one defines the generic type truck. They're very similar to each other. After that, we have the statements that define the nodes of the stroboscope network. And we see that we have a queue statement, a combi statement, a normal statement. The queue statement defines a queue. And in order to define a queue, we have to give it a name, such as a loader's weight. And we have to specify the type of resource that that queue can hold, in this case, loader. Notice that the name loader has already been defined previously as a gen type, and this introduces a very basic idea in stroboscope. We cannot use an identifier such as loader unless we have already defined it previously. So in this case, the gen type statement that defines loader must precede the queue statement that uses the identifier loader. The next statement after that defines a combi called load. Notice that there is nothing else defined about this combi. It doesn't say anything about the resources it can hold or its duration. Those will be handled later. The next statement, Q, defines the truck's weight Q, which holds the resources of type truck. Then we have the definition of 3 normal activities, and the only thing required there is to type normal and then to type the name that we wish to give to that normal activity, such as haul, dump, and return. After that, we have the definition of the links. The links in a network must be defined after we have already defined the nodes in the network, because as we will see, each link must specify the preceding node and the succeeding node that the link connects. So the very first link has to have a name. In this case, it is called TR1, and it goes from the node truck's weight, which is a Q, to the node load, which is a combi. The name of the link, TR1, can be anything that begins with a letter, but it is a good practice that we name the links using 2 letters and a number. The letters are usually mnemonic of the type of resource that flows through the link. So in this case, TR reminds us that through this link we have trucks loading. The next link, LD1, goes from loader's weight to load, and it carries resources of type loader. That's why its name, LD1, reminds us that it carries loaders. LD stands for loaders. The next link, LD2, is similar. It goes from the combi load to the Q loader's weight, and again, because it carries resources of type loader, we have given it the name LD2. Similarly, the next link, tier 2, tier 3, tier 4, and tier 5, they all carry resources of type truck. And notice that these particular links not only tell us the predecessor and the successor, but they also tell us the particular resource that flows through. So link tier 2 goes from load to haul, and it carries resources of type truck. Contrast this to link tier 1. Tier 1 goes from the Q truck's weight to the combi load. Because truck's weight can only hold resources of type truck, then link tier 1 can only allow resources of type truck to go through. So the Q specifies the type of resource that flows through the link. In this case, truck's weight specifies that the link tier 1 can only carry resources of type truck, so there is no reason to put the identifier truck at the very end of the first link statement. The following statements describe the startups of the various activities that exist in the network. And in this particular example, because it's so simple, the only description for the various activities that we see is the statement duration, followed by the name of the activity, such as load, followed by a formula enclosed in single quotes, and that formula defines the duration of the activity. So for activity load, the formula that defines its duration is given by a function called normal that takes 2 arguments, in this case 7 and 1.2. 7 is the expected value of the normal distribution, and 1.2 is the standard deviation. The statement name, the function name normal is a predefined function name in Stroboscope, and those are all described in the Stroboscope quick reference guide, which is available along with the installation of Stroboscope. The important thing to notice is that functions in Stroboscope do not use parentheses, they use brackets. So if you see brackets and closing arguments, that means that the preceding word, in this case normal, must be a function or an array, as we will see later on. So these statements, duration load, duration hold, duration dump, and duration return, define the durations of those 4 activities. 3 of them follow normal distribution, so they will have random durations generated by normally distributed random variables. The exception is dump, which is followed by just a number, 1.03, so dump has a deterministic duration. The comment line, initialization of queues, running the simulation, and presenting the results, begins the section that contains control statements. The first control statement is init, and init initializes the contents of the queue that follows to contain a certain number of resources. In this case, the first init statement initializes the queue track's weight to contain num truck, number of trucks. Num trucks in this case is a variable that has the value 11. So we are initializing the truck's weight queue to contain 11 trucks. The next init statement initializes the queue loader's weight to contain num loaders, number of loaders, and num loaders is a variable that has the value 3. So we're putting 3 loaders into the queue loader's weight. The next statement is simulate until. Simulate until is extremely important because it is the statement that instructs Stroboscope to actually perform the simulation. This is the statement that starts the simulation and defines the condition, the logical condition by which the simulation will end. The name simulate until tells us that the simulation will start and continue until a logical condition becomes true. The logical condition is the argument to the statement simulate until, which is dump.tot_inst greater than or equal to 7,500. What that logical statement says is that the simulation will continue until the total instances of activity dump are greater than or equal to 7,500. So the simulation will run until the activity dump starts 7,500 times. Notice that this controls the start of activity dump and not the end. So as soon as the 7,500th instance of activity dump starts, the simulation will end. After that, we have statements that are there to produce output that we desire to see. The first one of those is the variable total fleet cost, which is followed by a real formula in this case that calculates the total cost of the fleet of equipment that is being used in this particular example. The formula takes the number of loaders, multiplies it by the hourly cost of a loader, adds to that the number of trucks multiplied by the hourly cost of the haulers, and then the whole thing, the whole parenthesis, is multiplied by sim time, which is in minutes, divided by 60 to turn it into hours. So the end result is to multiply dollars per hour times hours, and that will give us the total fleet cost in dollars. The next statement, display, is the statement that displays something in the stroboscope output. Everything that appears within double quotes, in this case total working time followed by a colon, is simply a string, and it will be printed exactly as we see it there. Sim time is a predefined global variable in Stroboscope that tells us what is the simulation time at the end of the simulation in minutes. And dividing it by 60 will give us a number which tells us what the simulation duration was in hours. This is followed by the string, the text hours, which is enclosed in double quotes again. The next statement, display, shows a string, total equipment cost, which is enclosed in double quotes, followed by a number, which is the value of the variable total fleet cost, which will tell us what was the total cost of the equipment, and that is followed by the $ in parentheses to indicate that the total equipment cost is in dollars. The last statement, report, instructs a Stroboscope to print the standard Stroboscope report as part of its output file. When this input file is entered into Stroboscope and we press the button in Stroboscope that begins a simulation, we will see the following output file after a few seconds. This is the output file that Stroboscope will create based on the previous input file on the previous page. At the very top, we see the version of Stroboscope that was actually used to run the simulation and the name of the file that Stroboscope produced. In this case, it is called bridge1.sto, where ST stands for Stroboscope and O stands for output. The very first line tells us that the Stroboscope model that we have submitted is called bridge1.str. Files that end in str are Stroboscope input files. The number in parentheses gives us the actual seed that was used to initialize the random number generator for this particular run. The next two lines, total working time and total equipment cost, are produced by the display statements that we saw in the previous input file. The next line, statistics report at simulation time, is the very first line of the standard report that Stroboscope produces. So this line tells us that the simulation ended after 19,168 units of simulated time, which in this case represent minutes. After that, we have statistical information about queues, followed by statistical information about activities. For the queues, we see the two queues, loader's weight and truck's weight, the kind of resources they hold. The first one loader, the second one truck. The next column tells us how many resources are in the queue right now. So there is one loader in loader's weight and no trucks in truck's weight. The next column tells us the number of resources that entered that particular queue, including the number of resources that entered when we initialized that queue. The next column gives us the average waiting time in that queue. The next one, the average contents of that queue. And then the next three lines give us more statistics about contents, the standard deviation, the minimum, and the maximum contents of that queue. Then we have statistical information about activities. For each activity, the first column gives us the current instances of that activity. So, for example, dump has one instance currently going on, whereas return has currently 3 instances going on. The next column, total, gives us the total instances that were generated during the simulation for that activity. So dump started 7,500 times, which was the stopping condition for this simulation. As soon as we generated 7,500 instances of activity dump, then the simulation ended. Then we have the time at which the first instance of that activity started, and then the next column tells us the time when the last instance of that activity started. Now it's interesting to notice that activity dump had its last instance start at exactly the simulation time when the simulation ended, which is 19,168.619. Now, because it is rounded to 2 decimal points, the 619 became 62, but it is exactly the same number. After that, we have statistical information about the duration of the activity, its average duration, standard deviation, minimum duration, maximum duration. And after that, we have statistical information about the interval between successive starts of that activity. So we have the average interval, the standard deviation, the minimum, and the maximum. After that, we have information about the contents of the future event list at simulation time 19,168 when the simulation ended. And notice that we have several instances of activities that are still going on. Those are instances that have started but have not yet finished. So for activity whole, we have instance 7,500, and for activity dump, we have instance 7,499, and so on and so forth. The important thing to notice is that numbers of instances begin with the number 0. So the very first instance of dump had the number 0, so the very last instance of dump, the one that stopped the simulation, has a number 7,499. It is not 7,500 because the numbering begins at 0, it doesn't begin at 1. For each ongoing instance, we have the start of that particular activity instance and the end of that particular activity instance. And of course, the start must be less than or equal to the simulation time when the simulation ended, and the end must be greater than the time when the simulation actually ended. The second model is very similar to the first model and introduces a little bit more detail. In this model, the capacity of the average truck is assumed to be 26.67 cubic meters. The bucket capacity of the average loader is assumed to be 3.8 cubic meters. And as a result, to fill a truck, the loader must place 7 scoops into the truck. Consequently, the duration of load is given by the sum of 7 independent and identically distributed random variables, each of which represents the time it takes the loader to load 1 scoop of material into the truck. Thus, this probability density function depends only on the properties of the loader. It does not depend on the capacity of the truck. The capacity of the truck itself is reflected by the number of random variables that are added up, in this case 7. The duration statement for combi load is shown here as the sum of 7 random variables. The expected value of the time it takes to put 1 scoop into the truck is 1 minute, and the standard deviation is 0.44 minutes. Notice that by adding 7 random variables in this manner, the time it takes for each scoop to be placed into the truck is independent of the time it takes for any other scoop to be placed into the truck. The third model introduces soil as a resource. Notice that now we have 2 additional queues. On the left we have the soil to move queue, which is initialized with the amount of soil that is to be moved in cubic meters. And on the right we have the moved soil queue, which will contain all the moved soil at the end of simulation. In addition, we have 4 new links. They're all marked as SL followed by a number, where SL stands for soil, and the numbers just show the sequence by which the soil moves from its original location in soil to move to its final destination in moved soil. The new statements that need to be inserted into the stroboscope model are shown in this particular page. The first one is variable amount of soil, which is set to be 200,000, and that represents the amount of soil to move in cubic meters. The second statement defines the generic type soil by using gen type soil. And the third statement initializes the Q soil to move to contain an amount equal to amount of soil, which in this case is 200,000 cubic meters. In addition, we need to define the amount by which SL1 draws resources from the Q soil to move every time the combi load begins. That amount is defined by the statement draw amount, which is followed by the name of the link, SL1, followed by the quantity which will be removed from the preceding queue every time that the link draws an amount from soil to move. The number of draws by default is 1. Finally, instead of having the statement simulate until, we can have the statement simulate, which allows the simulation to run until we run out of resources. In this case, until the soil to move queue becomes empty, at which point the combi activity load cannot start, and of course no other activity will be able to start. All the trucks will finish haul, dump, and return. They will return into the truck's wait queue. Load will not be able to start again because soil to move is empty, and the simulation will be forced to start because the future event list will be empty and no activity will be able to start. Notice also that in this model the soil actually moves through the network. Precisely the amount of soil that is drawn from soil to move and moves through all the soil links equals a truck load of soil, which in this particular model is 26.67 cubic meters. The changes in the third model appear in the listing of the stroboscope model shown here. The new statements are shown with the label new with arrows pointing to the left. There are several such statements. There are two kinds of resources in stroboscope. Bulk resources are called generic resources, and individual resources, unique resources, are called characterized resources. Generic resources can be used to describe or to model resources that are bulk in nature, such as soil or cement or sand or materials of that kind, but they can also be used to represent trucks or loaders or people, which are by nature discrete resources and they are individually identifiable. Nevertheless, for simple models, we can use generic resources for all. In fact, EasyStrobe uses only generic resources and does not have characterized resources. This page has the definitions of all statements that are related to generic resources, followed by all the statements that are related to characterized resources. At this point, we will examine the statements that control the drawing process by which a combi activity preceded by a generic queue can draw resources through the link that connects the queue to the combi. For this simple example, the combi is called a load truck. The preceding queue is called soil to load and contains resources of type soil, and the link that connects them is called SL1. The definition of the link is done with the link statement, which gives the link a name and has the predecessor node, in this case soil to load, and the successor node, which in this case is load truck. To create an instance of a combi load truck, what must be true is that the enough attributes of all incoming links, such as SL1, must be true. So every incoming link has an enough attribute that we can change or define through an enough statement. The enough statement takes as an argument the name of the link, in this case SL1, followed by a logical expression. The default logical expression is shown here, and as you can see, it is a comparison that compares the current count of soil to load to the value 0. The current count represents the current contents of the queue soil to load, which precedes it in the name of this identifier. And the idea is that if this content is not empty, in other words, if it has any resources in it, if the amount of resources, in other words, currently in that queue are greater than 0, then there is enough resources that could possibly support the start of the combi load truck. In other words, the creation of a new instance of that combi. Notice that the enough attribute is an attribute of the link SL1. It is not an attribute of the preceding queue soil to load, even though what we are comparing here is the current contents of the queue soil to load to the value 0. We're not comparing an attribute of the link to any value. Let us assume that all the incoming links to combi load truck returned an enough value which is true. If that is true, then the activity, the combi load truck, would be able to create an instance, in which case the drawing process begins. The drawing process is a process through which the instance of load truck will draw resources through the incoming links, in this case through SL1, from the preceding queues, in this case from soil to load. This process is controlled by these three statements here. The first one is draw until, which controls how many times we're going to draw from the preceding queue through link SL1. So it is possible to draw multiple times from the preceding queue and put the resources, in this case soil, into the instance of load truck. Every time we draw through SL1, the amount of material that we draw is controlled through draw amount. Again, draw amount takes as a second argument the name of the link SL1, and the default expression is 1. In other words, by default, every time SL1 draws, it will take 1 unit. The default logical expression for draw until is shown here, and it says to draw until the number of draws through link SL1 is greater than or equal to 1. What this means in simple terms is that we should draw until the number of draws through the link is greater than or equal to 1, or in even simpler terms, we draw only once, because once we draw the first time, the number of draws will be 1, and it will be greater than or equal to 1. Every time we draw, we remove an amount of material from the preceding queue equal to this draw amount, the default being 1. In addition to drawing from the preceding queue, we also sample an expression given by the third statement, draw duration. Now, the draw duration expression, which by default is just the number 0, provides a mechanism by which we can sample from a random variable, such as how long it takes for a loader to put 1 scoop of soil into a truck. The way to think about this process is that each link, such as SL1, has a statistics collector built into it, which is initialized when the drawing process begins. Whenever we draw a draw amount, we also collect a draw duration via this expression, and we put it into the statistics collector of SL1. So if we draw 3 times through this link, we will collect 3 values of that particular duration expression. If this duration expression is to sample from a normal distribution, then our statistics collector in SL1 will have those 3 values, and we'll be able to use those statistics in determining the duration of load truck. This will be shown by an example in just a moment, and it will make the whole process clearer. The fourth model is the first to make use of Stroboscope's unique commands or statements for drawing generic resources from a preceding queue. These statements are draw until, draw amount, and draw duration. In this particular model, the duration of activity load represents the time it takes to fill a truck completely, but that time is not given by a single random variable, it is given as the sum of 12 normally distributed random variables. The mechanism by which this occurs can be described best by looking at the statements for link SL1. The first statement is draw until SL1 followed by a logical expression. The logical expression in this case is SL1 dot n draws greater than or equal to 12. In other words, the drawing process through link SL1 will continue until we have drawn at least 12 times through link SL1. That represents the fact that we need 12 loader scoops to fill a truck. The second statement is draw amount. Draw amount is followed by the name of the link, SL1, and then is followed by the amount that the link will draw from the preceding Q soil to move every time it draws. That amount is 2.22 cubic meters, and it represents the capacity of the loader's scoop. The third statement is draw duration, draw dur, which again takes as a second argument the name of the link, and then after that it has a formula, in this case simply the function normal with an expected value of 0.58 and a standard deviation of 0.33. That normally distributed random variable represents the time to load one scoop of soil from the soil in place into the truck. The drawing process occurs one scoop at a time, so the link SL1 will draw from the soil to move Q 12 times, and each time it will draw 2.22 cubic meters. Every time it draws, it will also sample a random variable from the distribution normal 0.58, 0.33 that represents the time it took for that scoop of soil to be loaded into the truck. The link has a statistics collector built into it, and at the very end we will make use of that statistics collector to define the duration of activity load. That is shown in the next statement, duration load, which takes as an argument SL1 dot sum draw duration. The sum draw duration is an attribute of link SL1, and it represents the sum of all the sampled draw durations that were sampled every time a draw amount of 2.22 cubic meters were taken out of the Q soil to move. As a result, the duration of load represents the sum of 12 normally distributed random variables, each one drawn or sampled independently of each other. Notice that the draw duration does not make simulated time go by. Only the duration of activities actually makes simulated time go by. The draw duration statement provides a mechanism by which we can sample the duration associated with each draw and then collect statistics over the entire set of samples. We can collect the sum, the average, the standard deviation, the minimum, and the maximum. The number of samples that are connected in this manner depends on the number of draws, and in this case the number of draws is controlled by the draw until statement. The draw until statement allows us to draw 12 times until the number of draws through link SL1 is greater than or equal to 12. The next page shows the Stroboscope input file that incorporates the new statements needed for Model 4. These statements are also shown with arrows pointing to the left with the label new in the middle. They are exactly the same as the statements shown on the previous page. The fifth model is the last model that uses generic resources to model this earth-moving operation. This model is different from the previous models in that the amount of soil that is drawn through link SL1 is now a random variable, and that the duration of haul is sensitive to the amount of soil that is actually loaded on a truck. If a truck is heavily loaded, then the duration of haul should be longer than if the truck is light. To model the fact that the amount of soil that each scoop of the loader places inside the truck is random, in other words, different every time, we modify the draw amount statement for link SL1 by multiplying the constant 2.22 cubic meters by a normally distributed random variable that has a mean of 1 and a standard deviation of 5%. What this means is that sometimes the scoop that is loaded into the truck carries more than 2.22 cubic meters, and sometimes it carries less. Because of this, the amount of soil that each instance of the load combi activity receives is different from any other instance, because it is the sum of 12 normally distributed scoops, essentially. And as a result, we don't really know how much soil each truck in each instance of load actually has received. Sometimes a truck in an instance of activity load receives more than its capacity of 26.67 cubic meters, and sometimes it receives less than that capacity. No matter what the amount of soil that each truck receives in activity load, that exact amount of soil, which we don't really know how much it is transferred into activity haul through link SL2. When we try to compute the duration of activity haul, we can now make the duration of haul be sensitive to the amount of soil that is actually loaded in the truck. This is shown by the statement duration haul, which is followed by the formula normal times haul.soil.count divided by 26.67. To understand this formula, we need to appreciate that 26.67 is the nominal capacity of the truck. The count of the soil in haul, which is given by the variable haul.soil.count, will be a number that is either more than 26.67 or less than 26.67. So it will be a fraction that it will be a little above 1 or a little below 1. That fraction will then multiply what we typically sample as the duration of activity haul, which is a normally distributed random variable with an expected value of 11.66 and a standard deviation of 0.3. So the amount of soil inside the truck modifies how long the duration of haul takes. The actual amount of soil that is drawn by the combi load through link SL1 is different for each truck. That amount of soil, which we don't really know how much it is, travels through the network through the links SL1 to SL4 and is deposited into the moved soil queue. Thus, each truck dumps a different amount of soil. The remaining models, starting with model 6, require the use of characterized resources as opposed to generic resources, and will be examined later. We shall stop at this point and examine the characteristics of models with generic resources in more detail, and once we've done that, then we will examine characterized resources, and we will return back to re-examine this tutorial starting with model 6. This page is a printout of a Visio file that contains a live Easystrobe model for the earth-moving operation that uses a hopper that was presented earlier. The purpose of this model is to show how an Easystrobe model can be converted into a stroboscope model by using the appropriate statements. We shall begin by examining the parameters that are defined in the EasyStrobe model. In this case, there are a couple of parameters here called S and H that has the values 4 and 20. In Stroboscope, those would be defined with these statements, variable S4 and variable H20. So we would use variable statements to define parameters. On the right-hand side, we have the definition of additional parameters that define the durations of the various activities. Notice that all the durations for this example are deterministic. In Stroboscope, those ordinarily would be defined using duration statements for each one of the activities in the model. In this example, we're primarily interested in the mechanism by which combi activities draw resources from the preceding queue. So let us begin with link SL1. Now, this particular link draws S units from the preceding queue soil to move. We would define this in Stroboscope by using the statement draw amount SL1 followed by the variable name S. So every time an instance of load hopper is created, it would remove from the preceding queue soil to move an amount equal to S through the link SL1. This is the equivalent of specifying S on the link in EasyStrobe. Note that the queue soil to move holds a resource called soil, which flows through link SL1 into instances of the combi load hopper. However, the important thing to notice here is that there is no outgoing link out of combi load hopper that carries the resource. At the end of each instance of load hopper, the resource soil that is carried by that particular instance will be destroyed. It will not be transferred to any other node. This raises the question of what kind of resources actually flow through this sequence of nodes that involve loading the hopper and loading the hauler. The answer is that the kind of resource that flows through this is called space. So we have a resource called space in space to hopper, which is initialized to 10 units. And we have a resource called space in soil to hopper, which is initialized to 20 units. And as you can see by the name of the links, SP1, SP2, SP3, and SP4, these 4 links carry resource of type space, which circulates or cycles through those particular 4 nodes. Let's now consider the conditions for load hopper to create an instance of itself. For load hopper to create an instance of itself, it will look at all 3 incoming links. There is one here, and one here. And we'll ask each one of those links to evaluate its enough expression. The enough expression are given by those inequalities that are written on each link. The one that is of interest to us here is the enough expression for link SP3. As we see here, that enough expression is given by that statement. And what it says is that SP3 has enough resources if the current count of the space in hopper is greater than or equal to S. So this link SP3 will examine the contents of space in hopper, which is the current count of space in hopper, and if it is greater than or equal to some value S, in this case the shovel capacity size, then it will return true. So this expression will return true. So the enough of SP3 will be true, and SP3 will allow load hopper to possibly create
an instance. Of course, the other links must also have enoughs that return true, otherwise the instance will not be created. When an instance of load hopper is created, then a certain amount of time will pass, and at the end of that, as we see in the EasyStrobe model, an amount of resource S is released through this link, SP4, into soil in hopper. Notice that in Stroboscope, there is no need to define a release amount statement for link SP4 and specify that the amount of resource that is released equals S, because Stroboscope has conservation of mass. If it has received S units of space through this link, each instance will contain S units of space, and because this link carries space, it will release exactly S units of space by default into the succeeding node. The other combi that is of interest in the conditions to start is load hauler. Again, load hauler has 3 incoming links from preceding queues, and all 3 links have to be queried to make sure that their enough attributes are true in order to create an instance of load hauler. The enough attribute for the link SP1 in EasyStrobe is given by this expression right here, which says that the contents of soil in hopper must be greater than or equal to H. The same thing is written using this statement here. In other words, enough SP1, logical expression. And the logical expression is that the current count of soil in hopper must be greater than or equal to H. So the current count of soil in hopper must be greater than or equal to H, which is identical to the requirement in EasyStrobe. If the enough attributes of all 3 incoming links into load hauler return the value true, then load hauler will create an instance of itself and the drawing process will start. Clearly, it will take 1 resource out of load space and 1 hauler out of hauler's weight, and then it will try to draw resources through link SP1 from soil in hopper. The amount of resources to be drawn is H, and that is described in Stroboscope using this statement, draw amount SP1 H. So H is the amount of resources that SP1 will draw from the preceding queue. After a hauler loads, then it hauls, waits to dump, and then actually dumps and returns and enters the queue hauler's weight. Notice that the activity dump does not have a link entering that contains resources of type soil. So the question becomes, how do we release a certain amount of soil into the queue soil in place that matches the capacity of the hauler? This is accomplished by specifying the release amount for link SL2. This statement here, release amount SL2H, is the statement that specifies that every time a dump finishes and releases resources through link SL2, link SL2 itself will create H amount of soil resource and deposit it into soil in place. Notice that it is the link itself, SL2, that creates the resource of soil and deposits it into soil in place. There is no soil resource in activity dump. This should be contrasted to the situation for combi load hopper and for combi load hauler. Both of these combis have preceding links that deliver a resource called space into an instance of, let's say, load hopper, And as a result, the instance of load hopper contains an amount of space equal to S. At the termination of an instance of load hopper, that amount of space flows out through this link, which carries space, and it goes into Soilin hopper. So there is no need to specify the release amount for this link, because by default, the instance of load hopper will release through SP4 as much resource of type space as it has received, which again equals S. The same is true for instances of the activity load hauler. When an instance of load hauler is created, it receives H units of the space of the resource called space through the preceding link SP1. At the end of an instance, the instance will release through link SP2 the entire amount of resource space that it has received through link SP1. So there is no reason again to specify a release amount for link SP2. By default, it will release as much resource space as the instance has received through SP1. This is the end of the description of this model. The rest of the nodes and functionality of this model is relatively easy to follow.